Hello, and welcome to my second tech update. For this update, I want to focus on a technology that already exists in the marketplace to some degree. This technology provides a whole product to a small niche of consumers. However, this highly energy-intensive process comes at a lofty price. For this update, I'm going to discuss new breakthroughs in water desalination. A UNICEF report made a prediction regarding water scarcity in India. There will be constant competition over water between farming families and urban dwellers, environmental conservationists and industrialists, minorities living off natural resources, and entrepreneurs seeking to commodify the resources base for commercial gain. According to the International Water Management Institute, by 2025, 1.8 billion people will live in countries or regions with absolute water scarcity. Most countries in the Middle East and North Africa can be classified as having absolute water scarcity today. By 2025, these countries will be joined by Pakistan, South Africa, and large parts of India and China. This means that they will not have sufficient water resources to maintain their current level of per capita food production from irrigated agriculture and also meet the reasonable water needs for domestic, industrial, and environmental processes. Desalination of seawater and brackish water is becoming an increasingly important means to address the scarcity of fresh water resources in the world. Decreasing the energy requirements and infrastructure costs of existing desalination technologies remains a challenge. By enabling the manipulation of matter and control of transport at nanometer length scales, the emergence of nanotechnology offers new opportunities to advance water desalination technology. Nanotechnology refers to new technologies developed at the nanometer scale. 1 nanometer is 1/1000th of a meter, which means that it would take 1 billion nanometers to equal 1 meter. Or, to give another way of looking at it, 1 million nanometers would make up one of these periods here. A cancer cell is about 10,000 to 100,000 nanometers. Bacteria are on the order of about 1,000 nanometers. A virus is 100 nanometers thick. Now we get down to the molecular scale of antibodies being about 10 nanometers and other proteins in the similar realm. A glucose or sugar molecule is just about 1 nanometer in diameter. And a water molecule is actually a fraction of a nanometer, 1/10th of a nanometer. In chemistry, you might hear this referred to as 1 angstrom. Here we have a graphical representation of a nanotube. And nanotubes are one of the, but not only, nanotechnological compounds that can be produced today. The increasing human population, combined with exploitation of water resources for domestic purposes, industry, and irrigation, has resulted in a shortage of fresh water supply in many parts of the world. Only about 0.5% of the 1.4 billion cubic kilometers of water in the world is accessible fresh water, which is furthermore poorly distributed across the globe. There are 26 countries that do not have sufficient water resources to sustain agriculture and economic development, and approximately 1 billion people lack access to safe drinking water. Particular regions with water scarcity include a significant portion of the Middle East, North Africa, Eastern Australia, parts of Central and South Asia, and the southwestern areas of North America. In addition, the projected 40 to 50% growth in human population over the next 50 years, coupled with industrialization and urbanization, will result in an increasing demand on the available water resources. While economic use and recycling of water for human and animal consumption can mitigate the problem to some extent, alternative sources of clean water are required to address this growing need. The main barriers to expanding desalination technology around the world are energy and infrastructure costs, which preclude the economical production and distribution of clean water. The energy required to produce 1 cubic meter of clean water range from about 4 kilowatt hours for reverse osmosis, between 23.9 to 96 kilowatt hours for multi-stage flash, and 26.4 to 36.7 kilowatt hours for multi-effect distillation, which includes pre-treatment, brine disposal, and water transport. Meanwhile, these costs do not include the infrastructure and extra maintenance costs of these large-scale processes. In 2009, desalination of 1 cubic meter of seawater and brackish water costs approximately 53 cents to $1.50 and 10 cents to $1, respectively. To meet the global demand for clean water, the total cost for desalination must decrease, which involves increasing the energy efficiency, minimizing costs associated with water pre-treatment, and decreasing the capital costs. Reverse osmosis is a growing seawater desalination technology due to the lower energy costs when compared to multi-stage flash systems. Recent developments in membrane technology, including biofouling reduction, scaling inhibitors, and material synthesis, along with energy recovery devices, have decreased the energy consumption of reverse osmosis plants. Currently, reverse osmosis plants account for 41% of the world's desalination capacity and about 80% of the number of operating plants. Reverse osmosis plants are now the most commonly installed desalination system in the world, accounting for 75% of newly built capacity, except for areas with vast energy reserves or high salinity feedwater. In reverse osmosis, desalination is achieved by applying high pressure to feedwater, forcing it through a semi-permeable membrane that permits the flow of water molecules, while restricting the flow of salt ions. For desalination to occur, the applied pressure must exceed the osmotic pressure of the feed water. Therefore, to achieve high water flux, a high permeability of the membrane is desired while maintaining high salt rejection. Flux refers to how much water can flow through the membrane in a certain amount of time. Membrane permeability depends on the membrane material, but the flux of water is also impacted adversely by biofouling and scaling. Furthermore, concentration polarization, i.e., accumulation of salt near the membrane layer, which also decreases the water flux. These should be minimized by appropriate system design. Carbon nanotubes provide an interesting solution to increasing process efficiency. Carbon nanotubes are an allotrope of carbon consisting of rolled-up sheets of graphitic layers. Carbon nanotubes are attractive for applications ranging from structural materials to electronics and energy storage due to their excellent thermal and electrical conductance, mechanical strength, and unique properties. Here we see an image of a carbon nanotube forest taken using scanning electron microscopy. Advances in synthesis procedures have recently enabled tight control of the diameters of carbon nanotubes, down to 1.6 nanometers and lengths up to a few centimeters. Such controlled synthesis techniques have led to the recent discovery of high water fluxes through the carbon nanotube membranes, opening the possibility of using such carbon nanotube membranes for reverse osmosis. Both molecular dynamics modeling and experiments have demonstrated that water fluxes through carbon nanotubes can be 4 to 5 orders of magnitude greater than those predicted by continuum hydrodynamics. This is because the inside of the carbon nanotubes are atomically smooth, resulting in relatively no frictional forces impeding the flow of the water as it passes through the membrane. In this picture, the carbon nanotube is shown in orange. The water molecules form a chain and pass right through. One interesting result from the orientation of the water molecules is that water in the nanotube doesn't freeze, even at hundreds of degrees below zero. If the nanotubes were assembled in a high density on a solid support, the structure could replace the semi-permeable membranes used today. Dissolved ions have an electrostatic charge which attract the dipole of water molecules. If the carbon nanotubes can be designed with a diameter that is less than the width of the hydrated ions, which is about 7.6 angstroms, then the material can act as a molecular sieve to desalinate water at a fraction of the energy. Currently, more work is needed to develop the material on the scale required for industrial application, but significant returns can be realized given the increasing demand. Thank you.